Please forgive me. Bismillahirrahmanirrahim. Assalamu alaikum, and welcome to Lecture 4 of the Celestial Lessons. It is we have a week left, about a week left of the Ramadan, and the moon is in its past its third quarter, so it is now a waning crescent, and we're waiting for it to become anew. I'm sorry that I don't have any photos to show this time. The sky over Denmark has been quite overcast these days, so I have not had the opportunity to take a photo of the moon. In today's lecture, we're moving towards cosmology, or the evolution of the universe as a whole. The material is rich and varied. It may seem disconnected at first. Along the way, we introduce the necessary physical concepts. So please be patient. We will end on a light note that I'm sure is relevant for everyone. In this lecture, because it's so rich and varied, I found it necessary to include a roadmap. We begin by thinking about measuring speeds in different frames and the speed of light, picking up from last time. We find that it leads to a change in the understanding of, we find that this thinking leads to a change in the understanding of space and time, to special relativity. We are then led by thought experiments to general relativity, which also describes gravity. After this, we go interstellar, first in our own galaxy. We talk about the stars, and we find amongst nebulae in our galaxy that some of the nebulae are not nebulae in our galaxy at all, but are different other galaxies. We find from other galaxies that the universe is expanding, and we ask about the farthest we can see, and finally what this light tells us. So first an elaboration on where we left off in lecture 3, and then a preparation for the main body of lecture 4. We ended with the equations governing electric and magnetic fields, Maxwell's equations, and that they predict electromagnetic waves. These waves travel with the speed of light, c. But with respect to whom is it traveling with the speed of light? Because measured speeds depend on the frame of reference. We can consider two cars that travel in the same direction with the same speed. To each other, it is as if the other is not moving. So speed is relative. It's relative, and it depends on the frame one is in. If speed is relative, what about the laws? We imagine that we place ourselves in the room of a ship that's sailing steadily. And here we have a game of table tennis. The ball in the game of table tennis on the ship, on this sailing ship, is behaving in the same way as on land. So we see that we do not notice that we are moving. The laws of motion are the same as before when moving with a steady velocity. So the laws of motion are not changed by being in a frame that's moving with a steady velocity with respect to the old frame. The objects are still, or they are moving steadily in lines. We're not forced. This was Newton's first law. There are, however, other frames, accelerated frames. For instance, an aircraft taking off, accelerating. Free objects seem to be sliding back, even though nothing is forcing them. So the objects are not still, nor are they moving steadily, they are accelerating. But where is that force? We know that a force makes an object accelerate, but here there does not seem to be any force. So the objects are spontaneously or as the flight is accelerating, the objects seem to be going backwards or being pushed back. We can understand this phenomenon if we zoom out and consider the situation from outside the aircraft. Objects want to stand still or move steadily in straight lines, but the frame itself is speeding up or accelerating. Someone fixed in the aircraft, someone who sits in the aircraft, is misled because he's in a strange frame. He thinks that there is a hidden force acting on all objects, pushing them back. But really, objects just want to be at rest or move steadily. And like a broom, the aircraft sweeps past the objects. Some objects get stuck on one of the seats and then get pushed forward. So this shows that experience in accelerated frames is quite different from steadily moving frames, and the laws are different, or at least they should be applied differently. Another example is the turning car. It's familiar to all of you. This is also an accelerating frame. The car undergoes a curved motion. The car is turning left. Everything, however, seems to be sliding to the right. Why is this? From outside the car, it is clear why. All objects really want to move steadily or stand still. In this case, move steadily forwards. But the car itself is turning left. So inside the car, because it is turning left, their will, or the will of the objects to continue straight, steady motion, is interpreted as a push to the right. So we will not consider accelerated frames for now, just the steady motion, the frames that move with a steady motion. And this gives us an introduction to special relativity. One, if the laws are the same for everyone, whether moving or not. And two, if electromagnetic waves travel at the speed of light according to laws, then we can combine these two and say, well, then light is seen to travel at the same speed no matter what the frame, because the laws are the same for everyone, and the laws say that light travels with the speed of light, and so everyone sees light travel with the speed of light. This seems very trivial, but it is actually not. So the light speed is always the same for everyone. Accepting this leads to three effects, which we will discuss. It is the relativity of length, duration, and simultaneity. Two viewers moving with respect to each other do not agree on lengths, durations, or whether two events occurred at the same time. So compared to a still viewer, a moving viewer thinks that lengths are shorter. It's called length contraction, that durations are greater, time dilation, and simultaneous events to the still observer happen at different times for the moving observer. This is quite strange. To illustrate this, let us go through the reasoning behind the time dilation. So we consider a thought experiment, and we consider the same events from two different perspectives. And we will focus on the clock. So we have two viewers, one inside a spaceship and another one outside. The inside viewer has a clock. He's made it out of light. He measures time by a light clock or a light pendulum. The ticking is given by the light bouncing between two mirrors, and one cycle is one return of the light. Since light moves at a constant speed, this is a very irregular clock. So let's first consider the ticking of the light clock inside the spaceship. So to the inside viewer who is at rest with respect to the clock. This motion is in a vertical line. But outside the spaceship, he will be moving. And so the light, so the clock will be ticking, and due to the motion of the spaceship, the light is tracing out a different path, the path of the slanted line. The other one was in the first case it was a vertical line, and here it's a slanted line in the second case to the other observer. So the inside observer sees a vertical path. The outside one sees a slanted one. And to understand the phenomenon and to show the phenomenon of time dilation, one really only needs to know the theorem of Pythagoras. So we see that there is a triangle here and a triangle here as well, and the same triangle in fact. We know that the hypotenuse of a triangle is the longest side of a right triangle. So the ticking takes longer according to the outside observer. It's shorter according to the inside viewer. So the outside viewer sees moving clocks tick slower. The outside viewer is moving with respect to the clock, and he measures more time to have elapsed than the still viewer. And it is because we have a path that's simply taking longer to traverse, and it has a constant speed, and it's more by a factor called gamma, or often denoted gamma, which depends on the speed of the spaceship, of the observer, or the moving clock. So that was time dilation. Another effect of special relativity that changes our perception of space and time is this experiment that illustrates, or this thought experiment that illustrates the relativity of simultaneity. So here we consider two viewers, again, an inside viewer, a viewer inside a right moving train, and another one who is still outside. And so the inside viewer sits in the middle of the train. This is very important. So his distance to the two trees is equal, and the distance from the outside viewer to the two trees is also equal. This is very important for the experiment. This is a thought experiment, so we can construct it any way we like. The outside viewer sees two lightning bolts strike the two trees at the same time. So the two lightning bolts going off, and they strike the two trees at the same time. And just at this time, the train is right in the middle, so that he sees the train centered in front of him. So the light travels to the outside viewer and from both trees and reaches him, and both bolts, or the flashes of both bolts, reach him at the same time. So he concludes that they happen at the same time. But because the inside viewer is in a moving train, he will have moved closer to the lightning bolt to the right. So he will meet the lightning bolt from the right. He will meet that one before the left one. But the inside viewer sits in the middle, and the light has traveled from the two ends. The distances are the same, yet he sees one before the other. So this means that they cannot both have been emitted at the same time to the inside viewer. So his perception of what happens at the same time is different. So the perception of the moving observer is different from that of the stationary observer, or the perception of that of the inside observer who's moving is different from that of the outside one who's still with respect to the events. Another prominent effect of special relativity is the Doppler effect. We first recall that light of a particular color is a wave with a particular frequency. But what happens if the emitter of light is moving? if the emitter of light, while he's shining that light, or while it is shining, if he's moving towards us, what we see is we see the light at a different frequency, at a higher frequency. So if this was the light if this black band, or if this corresponds to the frequency of the light that he's sending while he's at rest, because he's moving, we will now observe it to be at a different frequency, at a higher frequency. Higher frequency means bluer light, and so we say that it's blue shifted. So light has been blue shifted, or sent towards the blue end of the spectrum. If the emitter is moving away from us, we see the light at a lower frequency. So we saw this was where it was originally, and we now see it at a lower frequency. Lower frequency means redder light, so it's shifted towards the red end of the spectrum, and we say that the light has been redshifted as a result of the moving observer. So we can use this to measure velocities of objects by the shift, if we know the color of the light they were originally emitting. In order to understand some of the other effects of special relativity, we introduced the concept of momentum. So fixed or conserved quantities are good to have when analyzing motion, because if they're fixed, or if they don't change, that means before or after an event they're the same. They don't change. So before and after a collision of the billiard balls, we might find the quantity to be the same. One fixed quantity in a closed system is the total momentum of the system, and the momentum of an object is normally denoted p, and it's the mass times the velocity. And to get the total one, we just add up all the momenta, or the masses times the velocities, and we take the sum. And before and after the collision of the billiard balls, the total momentum is the same, so it can help us analyze the motion. Another more familiar concept, though perhaps not understood not understood by everyone in technical terms, is the concept of energy. This is another conserved quantity, the total energy. Energy can be kinetic or potential. Kinetic energy is associated with motion. The kinetic energy is equal to half times the mass times the speed squared. Potential energy is associated with an object that is inside a field. It can be a gravitational field, it can be an electric field, or any other force field. It refers to the unreleased, hence potential energy. For instance, a book on a table can release potential energy by having its barrier, the table, removed. So it will fall and convert some of the potential energy into kinetic energy, but the sum will be preserved. Total energy stays the same. So having introduced that concept and having seen that moving viewers will disagree about durations and lengths and whether events happen at the same time, there are other effects of special relativity that we will not prove, but that I do mention here. A twin that travels will be younger than the twin at rest. The momentum that we referred to earlier actually gets a factor. It's not m times v, but in special relativity it gets this factor of gamma in front. And what one sees when one changes frames is that energy and momentum also change into each other, but they don't change just arbitrarily. They keep this particular relation, the square of the energy minus the square of the momentum multiplied by a factor, equal to a certain fixed quantity, the mass. It turns out to be the mass of an object, of the object in question. For objects at rest, there is no momentum. And so one sees that E squared is equal to m squared times c to the fourth power, and this is also the same as E equals mc squared, which is that famous equation. So mass becomes a part of energy, really, whereas it was separate before. So that was special relativity, and let us now discuss general relativity. General relativity is a generalization, that's why it has the general in it, of special relativity to include gravity. The key insight is to find a frame. So the insight, if we have to summarize general relativity to just one concept, it is to find a frame in which to cancel gravity. And once you've canceled gravity, you no longer have to worry about it, because now you can use special relativity that you have already developed. And so we get to this ironic question. Is it not ironic how, when gravity is the only force that acts upon us, it is the only force that we cannot feel? And let me illustrate. So suppose you are in a lift and the wires that keep the lift suspended are cut. So you're falling. Now take off your wristwatch. What happens to the wristwatch? Some people imagine that it will go up, fly upwards. But actually it's not going up, it is floating right next to you. So if something is floating right next to you, that means that the action of gravity has been cancelled, because we know that gravity usually makes things fall. So if you let yourself freely fall and analyze the physical situation from that point of view, you need not worry about gravity, and you can apply special relativity. And you know how the falling frame and the stationary frame are related. So you can transform back to the other frame after having done the gravity-free analysis to obtain the answer. And going back and forth between these frames looks mathematically like going from flat space to curved space. So this realization makes us make the final claim, which is that mass and energy, which we know to be responsible for gravity, that they curve space-time. And gravity becomes a manifestation of the curvature of space-time. Motions of objects happen to be shortest paths on this space-time, so it's quite elegant. What are the effects of general relativity? Some of the consequences are that just as gravity curves the paths of moving bodies, we think of a fountain, it also curves the path of light. This is called gravitational lensing. It is a deflection of light due to gravity. So we see that light is really behaving in the same, so not quite in the same way, but has similar properties as everything else. Gravity, this is another consequence. When one works out the details, it behaves differently from Newtonian gravity. And we know from before that the predictions of planetary orbits were governed by Newtonian gravity. And we derived, or we saw that I said that the elliptic orbits of planets were a result of using Newton's Newton's law for gravity. So if there are changes to the predictions of the planetary orbits, if general relativity predicts this, we might it may be that it can be seen in the solar system, and in particular, it predicts an effect that the semi-major axis. So recall that an ellipse had two axes, one that was a long axis and a short one, and the half of so the long axis, since the ellipses points, or the ellipses is not as a circle symmetric, so it points in a certain direction. And so the prediction of general relativity is that this axis rotates over centuries. So the semi-major axis of Mercury rotates over centuries. While it is still performing this elliptic motion, there is also something that changes, or that rotates the ellipse. Another effect is that light is redshifted as it leaves the gravitational field. So it's much like a ball that is thrown up in the air. It is the ball is losing energy in the same way the light is losing energy as it is leaving a gravitational field. This brings us to the main body of the fourth lecture, where recall that we would like to go to the edge of seeing, as I've called it, as I've called the lecture. So we were in lectures 1, 2, and 3. We were looking at the motion of planets and the sun and the moon. So let us now consider the stars. The stars are very far away. Let's compare. If we look at how long it takes light to reach the moon, it's about a second. So the moon is about a second away. The sun, our nearest star, it is the sun, a star, but we treat it especially. However, it is a star. It's about 8 minutes away. So light takes by light it is 8 minutes away. So light takes about 8 minutes to travel to the sun. Now the nearest star to the sun is Alpha Centauri. It takes about 4 years by light. It takes light 4 years to reach Alpha Centauri from the sun. And Alpha Centauri is perhaps unknown to sky gazers in Cambridge, for obvious reasons. It does not appear above the horizon. So Alpha Centauri is this star that has a white circle around it. It is below Scorpius and below Sagittarius and below Libra and near the Southern Cross. So it actually, we don't see it on these latitudes. However, for observers or for viewers on the Southern Hemisphere, they don't have the luxury of having the North Star. So they need to find a replacement. And so Alpha Centauri can be used to find south, to find the direction south. And once one knows south, one can find the other directions as well. So the way it's done is one takes Alpha Centauri and its neighboring star, and draws a line that's perpendicular to the line between the two stars, and then one draws a line through the Southern Cross, and where the two lines intersect, that will be direction south for viewers on the Southern Hemisphere. So it's not there is no star that is exactly or is pointing in the southern direction. So they really have to use this technique in order to find it. It's more cumbersome than for viewers on the northern hemisphere. So we have that we heard that the nearest star, Alpha Centauri, takes about 4 years by light. But we say 4 light years. That's a distance, not a time. The distance that light travels in 4 years. So that's 4 light years. But I said 4 light years. How do we know? And we know by the concept of parallax. So this is a technique used to measure the distance to a star. So we would like to know the distance to a star X from the sun. So it is this distance we would like to determine. And there is a There is we consider first a background of stars that don't move, that don't appear to be moving. So in December, from Earth, we note where it is pointing, what direction it's pointing in on this sphere, on the celestial sphere, where what point at the in the background of stars it's pointing towards. And then we wait half a year until the Earth is on the other side of the orbit and make the same measurement. The star, as seen from Earth, is now pointing towards a new place on the background. You can see these two places, and now this is exaggerated, one will not see such a large effect. This points towards a new place. And this angle can be measured. So if we know this angle, we know that this angle is the half of that angle. And we know one of the sides, that is the distance from the Earth to the Sun. And this is a right triangle, so we really have two angles, and we have the third as well, because we know the sum of angles in a triangle is 180 degrees, and we have one side, so we can use trigonometry to determine this distance that we are interested in. But how large are these angles? These parallax angles, they're called. It turns out they are arc seconds large. This is very small. 1 arc second is 1 degree. Divided, so the 360 degrees in a circle, 1 degree, so a circle divided in 360 pieces, that's 1 degree, and we have to divide this by 60 and then divide it by 60 again. So it's 1/3600th of a degree. That's 1 arc second. So we need a very precise setup to measure it, and it has been done amazingly. And they've gotten much more sophisticated than this. A parallax effect of 1 arc second corresponds to a distance that's 3.26 light years. So astronomers use this as a convenient unit of length. They say 1 parsec, that's what they call it. Parallax, I suppose, parallax arc second, that's how the word was formed. And 1 parsec is 3.26 light years. So it's a unit of distance, 1 parsec. There is one thing one should note. That's something that's perhaps attractive at first. Just because two stars are near each other in the sky or in the same constellation, it does not mean they are near each other physically. An example is Orion's belt, where the 3 stars in Orion's belt are 817 or 800, 2000, and 900. So one is about 800, the other one is about 2000, and the third one is about 900 light years away. So you would think that those 3 stars were related to each other because we say that's part of Orion's belt, but maybe the constellations are some fanciful groupings of the stars. It doesn't say anything about the distances. And before we talk about the workings of these stars, we talk about atoms, because the key to the function of the star is the nuclear structure. And the atoms are units or elements of matter. The simplest atom is hydrogen, and it is the most common element in the universe. Atoms have a nucleus and an electron or electrons bound in shells around it. So the simplest nucleus is just 1 proton. It's a positive charge, and then one has 1 electron around it. That's a hydrogen atom, an equal but negative charge. So the electron carries an equal but negative charge compared to the proton. And atoms are distinguished by the number of protons. So helium has 2 protons. And helium also has 2 electrons to balance the charge, because opposite charges attract. the nucleus can also contain neutral particles, and these are called neutrons. So helium in general contains additionally 2 neutrons, so 2 protons, 2 neutrons, and 2 electrons around it. One type of helium. There are other types as well. So that was the atom. Let us first discuss the bound electrons. Each electron shell corresponds to an energy level. Really, the electric attraction between the positive and positive nucleus and the negative electron is responsible for the difference in the energy levels. There is a lowest level called the ground state. Higher levels are called excited states. A transition from a low state to a higher state is accomplished by the absorption of a unit of light, and this unit of light is called a photon. So, but conversely, that was going from a low state to a high state with the absorption of a photon. There is also the other way around, that going from a higher state to a lower state is followed by the emission of light, or the emission of this packet of energy, the photon. And what energy does this photon have? It depends on the energy difference between the levels. And the higher the energy of the photon, the higher the frequency of the photon. So here one sees some of the lines of hydrogen. Only very specific frequencies are emitted, and these correspond to the different shells and their very specific differences in energy levels between them. Now, those were the bound electrons. If the electron receives a high enough energy from outside, it can become free. The atom is then ionized because one has a system of disintegrated atoms, or an electron that is not bound to the nucleus, and a system of disintegrated atoms, nuclei and free electrons, is called a plasma. We can reach this state by heating enough. Those were the electrons and the energy levels. Now let's go to the nucleus. The nucleus consists of protons and neutrons. They're held together by the short range, it's called a strong nuclear force, which is a complicated force that we understand the principles of, but in practice it's very it's a very complicated force that we understand the principles of, but in practice, since it's a strongly coupled system, it's difficult to fully understand. Some nuclei are unstable, and they can split. This is called fission. They can also decay. There is alpha decay, which is the emission of a helium nucleus, 2 protons and 2 neutrons. There is beta decay, where the neutron turns into a proton. It's a transmutation, and this is actually what's responsible. Underneath it is actually the weak force called the weak force. So the neutron turns into a proton. The beta decay is that the neutron turns into a proton and an electron that then gets ejected. And so having 2 nuclei together, since they're both, if one has 2 nuclei together, they're both positively charged, they actually repel each other. However, if we can get them close enough to each other, the strong force, the strong nuclear force, can begin to act. Since it's a short range force, it can, if they get close enough to each other, the strong force can begin to act and they can fuse. So how does one accomplish this? Because we have two positively charged nuclei, and they repel each other by the uh, by the electrostatic force. What we can do is we can give them a high enough speed so that they are overcoming this repulsion. And to give atoms high enough speed means that one to give them a more kinetic energy. This is equivalent to heating them up. So this process of nuclear fusion, where one brings together or fuses nuclei, releases energy. And this is what powers stars, the nuclear fusion. So it's kind of strange that we had to await all these developments in atomic physics and nuclear physics in order to understand what this grand structure in the sky, how it's really operating. What's important is firstly is gravity. It's an attractive force and actually an unstable force. It concentrates matter because it's attractive. So the more matter is concentrated, the stronger it concentrates. So it has this unstable effect. It's called the gravitational instability. So stars are thought to arise from the gravitational collapse of a cloud of gas, mostly hydrogen or helium. But this collapse is stopped by the pressure from the gas that gets heated in the meantime. This gas is heated first by the contraction of the cloud. So there is a release of gravitational potential energy as it's falling, just like a book is falling and has some energy. So this cloud gains some internal energy, or is heated up, and this then counteracts the attraction of gravity. So there is a balance between the two forces, and that's keeping the star stable for a while. If the temperature is high enough, an ignition of nuclear fusion happens. Since if we get a temperature that's high enough, now there is a chance that some of these nuclei will fuse and they will release some energy, and a lot of energy is released by nuclear fusion. Now, and this nuclear fusion then releases energy that heats the gas and produces the light that we see. But something happens when stars, now they're running on fuel, they're running on the conversion of hydrogen into helium. But at some point they will run out of fuel, they will run out of hydrogen. So they will have to switch, or there necessarily switches to fuse the higher nuclei, so helium into heavier nuclei. But this will terminate at some point. And this transition to a different fuel causes changes in the star, so that the star does not shine in the same way at all times. So those were the stars. Looking at the sky with a telescope, we can see more than planets and stars. There are also nebulae. And a nebula is a cloud-like extended object on the sky, such as this one. Some of the nebulae, like this one, they are glowing gas and dust heated by an active star in the middle. Some nebulae, one can see that it was a broad category, but really one can make a subdivision. Some are cold clouds of gas, thought to be the birthplace of new stars. Remember that I said that we think that stars form by the collapse of clouds, and these clouds are cold. So this is the Orion Nebula. And some nebulae are the remains of a supernova, a star explosion. Recall that something had to happen in the end with the star. If it one possible destiny of a star seems to be that it collapses, and collapses under its own weight, one can say, and there is an explosion, a supernova explosion, and this is a remnant, a supernova remnant. This is the Crab Nebula. Now, one should be cautious. I think these are not real colors. I think these were colors that were false colors, but they still reflect the variety that one sees, because one does not, I don't think one sees this optically, but in X-ray. So they reflect the variety of the radiation that's coming from this this remnant. That still, even though the supernova happened centuries ago, there is still something remaining. And then there are the misidentified nebulae. Until last century, it's not later than that, others were misidentified. These ones, for instance, there are others. These are the large and small Magellanic Clouds. It turns out that they are other galaxies. So we are not alone. The galaxy, there is not just one galaxy, our galaxy, the Milky Way. There are other galaxies as well. So the solar system and the stars around us are in a galaxy, and it's called the Milky Way. Galaxies are concentration of stars and gas and dust in an otherwise dilute universe. And there are roughly tens of billions of stars in a typical galaxy. And I think this is a photo from Chile, where one has taken a photo of the sky with long exposure, and one can see the Milky Way, unresolved stars, and gas and dust on the sky visibly. So galaxies can have different shape, reflecting reflecting a different formation and age and evolution. The Milky Way is a barred. Has a bar. Is a spiral galaxy, but there are also less structured galaxies called elliptical galaxies. The rough size of galaxies, just to give you an idea of the scales, is 10,000 parsec, 10 kiloparsec, or about 32,000 light years. That's quite many distances to Alpha Centauri, and one is still within one galaxy. Spiral galaxies are ordered. The stars circle the center in a circuit that takes roughly 100 million years. So even the fixed stars that we see on the sky that we think are really fixed, they are also moving themselves. And so all the constellations over time will change in shape. The most popular of the nearest and the most prominent is, it was once thought to be a nebula. It was categorized as M31. So there was a catalog called, compiled by Messier, and this is the Messier catalog, and it got the number 31. It was thought to be a nebula, but it is the nearest very large galaxy, and it is the Andromeda galaxy. It is in the constellation Andromeda. So it points, it's outside of our galaxy, so it's not near these stars, but it is, if one has to point towards it or travel towards it, one would go in the direction of the constellation of Andromeda. And if you could see it clearly, it would be larger than the moon in the sky, but it is faint, so you don't see it. It's amazing. And this is not the end. Here I give you some of the more modern data or representation of the data. This is a survey. This is the Sloan Digital Sky Survey that looks in particular regions of the sky. So one sees some black regions where it hasn't been looking, but then the other regions, there it has been looking, and one can see a lot of structure. And actually, each dot is a galaxy. And the rough distance between galaxies, the rough distances are megaparsec, or millions of light years. Recall, we had thousands of light years, or tens of thousands of light years for their size, and for the distances between galaxies, we have millions of light years. And we see that, so this is a quite late universe, right? We are, it's in our, it's not the early universe. This is the late universe, and this is what the late universe looks like. One sees even structure on very large scales, and these structures are thread-like or filamentary. And these filaments are made of galaxies, and there are also places where there are holes of various sizes. These are called voids. The filaments are thought to arise from the attraction or clustering due to gravity. Recall, the gravity is attractive, and so so gravity has this attractive property, and so it causes things to cluster. So we can look at the light from the other galaxies, and by looking at the light, and normally one would see those spectral lines that I showed from hydrogen, for instance, or from other atoms, and one in general sees that the spectra from the other galaxies, the light that's coming from the other galaxies, is redshifted. So all galaxies that we look towards seem to be moving away from us, or in general, or all of them. And furthermore, the more distant they are, the faster they're moving away. This was an empirical law to begin with, something that one just discovered by compiling all the data. That the velocity of the redshift, or which was inferred from the velocity which was inferred from the redshift, seems to be proportional to the distance to that galaxy. And the constant of proportionality is called the Hubble constant. It was then realized that there may be another source of redshift, and this is the expansion of space. However, it can also be both. So it can be that space is expanding, which we think to be the case today, and we think more than that, but that I will come to later. We think that space is expanding, but also the galaxies that live on that space are moving. So you can get both effects. So you can get a redshift due to, or a blue shift due to the motion of the galaxy. It's called a peculiar motion. And you can get an effect due to the expansion of space. So in fact, this problem of the additional motion of galaxies still complicates the interpretation of data today, because how is one going to disentangle the two? And this is still something that's a research problem. The expansion of space simply means that all distances are increasing with time. So no center or no distinguished point was needed in order to talk about expansion of space. Sometimes people picture that it's expanding from a point, and I think this is a misconception. It simply means if you take all distances between objects, what the expansion of space means is that you simply scale those distances. You multiply them by a scale factor. It's denoted A. The Hubble constant then measures the rate of change of this scale factor today. And so one can go to general relativity and ask, if we assume that there is a uniform universe that is alike in all directions, what does general relativity predict? And it predicts that space expands in time, or that there is an expansion of space. And this rate of expansion varies with time, and it depends on the composition of the universe. Radiation and ordinary matter expand the universe. So just the presence of radiation or matter, light and matter, makes the universe expand, the presence of an energy density. But the presence of these components really make it slow down with time. So it's expanding, but it's expanding at a slower and slower and slower rate. Today we're also operating with dark energy, which is quite elusive and mysterious. This is a component thought to be able to make the expansion accelerate. There are other consequences of the expansion of space. It is not just the redshift of light. It also dilutes and cools the universe. So the universe has been expanding, or if it is continually expanding, it suggests that the early universe was both denser and hotter. And the earlier the universe, the denser and hotter it was. There's another fact that we must appreciate when we established in lecture 3 that the speed of light is finite. That light it takes time for light to reach us. Since light has a speed, it takes time for it from a distant object to reach us. So the picture we get from a distant object now is really from the past, and the more distant it is, the earlier. We can ask, is there a limit? Is there an earliest time that we can see, and times earlier than that time are for some reason veiled? And this I would like to call the edge of seeing. So it turns out that there is a relic from the early hot universe. It is called the cosmic microwave background, and it is radiation from the early hot state. But it has been cooling down, or it has been redshifted. The radiation has been redshifted or losing energy. So it is now low frequency microwave radiation, whereas it used to be more than microwave radiation before, higher frequency before. So this light is coming from the earliest time that we can really get. It's a very distant place. It's light emitted, we think. Now there is, it's quite, I should really have cautioned all this discussion, but to say that many assumptions go into this, and this is a very simple analysis. But I think the physicists are doing sometimes, well, maybe not always, but doing their best with what they have. And many of these ideas, as you've seen in these lectures, are quite creative, and a lot of thought was put into it. So it is the earliest time that so the cosmic microwave background is very old radiation. It's 380,000 years after the beginning, we think. That's when it was emitted. So we look to that farthest distance, and that really refers to an early time. And we ask, what about before that time, before it was emitted? What was the universe like then? But the universe, as we saw, has been cooling down, or has been expanding and cooling down and becoming more dilute. Before that time, it was so hot that the neutral hydrogen gas that pervades the universe disintegrated due to the heat. It disintegrated, freeing the electrons. So the electrons became free, and they could then disturb the light. So this moment that we have, that we get the cosmic microwave background from, is really the earliest moment that light could be emitted undisturbed. And information coming from earlier times is really veiled by the free electrons in the plasma. So they are veiling, and they are disturbing the light, just like a very thick, opaque glass, in such a way that we really don't see anything other than this. And looking at the cosmic microwave background, we can then look at its properties. Is it the same in all directions? If we point, if we measure the the radiation coming from a certain direction, is it the same as another direction? And it turns out that it is almost the same in all directions. Now, this is after one has cleaned. There are many foregrounds and so on. There are many other things that can also emit microwave radiation. One has to make sure that this is it's clean of that, to not make a wrong, to not make a to not conclude the wrong thing, because the data is not clean. And the light is, so if we really have the celestial sphere projected onto this plane, where with the galactic center in the middle, the light, it is as if the light is almost the same in all directions, and the light is, it's as if it's coming from a state that had a that had the same temperature in all directions, but had a very low temperature, little more than minus 270 degrees Celsius. So a very, very low temperature. Recall that it has cooled. But when one gets a more sensitive instrument and looks closely, it reveals, now in this case, I think it's the opposite. It reveals this would be a hotter region, and this would be a colder region. And so this is a millidegrees that one really, of temperature that one really picks up. And so there is a region, I think this one is pointing in the direction of Leo, the constellation Leo, but really beyond, everything is beyond our galaxy, but in that direction. And it, so it reveals that there is a hot part, and in the opposite direction there is a cold part. So this suggests that what has happened is that the solar system is hurled through space at more than 300 kilometers per second. Then one gets a Doppler effect, where the light coming towards us is perceived as being of a higher frequency and coming from hotter radiation, and the light from behind us is we are moving away from it, and so we are seeing it as colder. So we use this to conclude that perhaps now it may also be that it may also be due to other things, but this suggests that we are really hurled through the I mean, our solar system is really moving very, very quickly with respect to this radiation. So yes, the radiation in one direction is blue shifted, hotter, and in the other direction it is red shifted, colder. Now one can subtract this and ends up with a weak, this is almost micro Kelvin or micro Celsius, a very weak grainy signal in the radiation. And these are thought to be the disturbances due to the early seeds of matter that were present when this radiation was formed a long time ago, when it was emitted, not formed but emitted. So due to gravity, these so we see we see a weak signal. So that means that these seeds were not very strong in contrast. Due to gravity, these seeds grew in mass to eventually form the embryos of galaxies, or the galaxies that we observe today. So they were really a precursor to this large-scale structure that we observe today. So what one sees due to this these weak disturbances is, unlike the late universe, which we saw to be clustered and full of structure, the early universes are like it without form. There were only small disturbances in the radiation. Analyzing more this radiation, we reach some strange conclusions. General relativity in general allows for space to be curved, but it seems that space is flat, and in flat space, angles of a triangle add up to 180 degrees. In principle, it could have been an open universe or closed open space or closed space, corresponding to open universe and a closed universe, where angles of a triangle do not add up to 180 degrees, but these these angles have a deficit, and that depends on the area of the triangle that one is drawing. And another conclusion is that from analyzing this radiation is that it seems that only 5% of the composition of the universe is matter that we know. 25% is dark matter. It's like the matter that we know. It behaves in the same way, but only it does not emit any light at all, so it's invisible. And the rest is we think what's called due to a cosmological constant, or an elusive dark energy that's responsible for a late time acceleration of the expansion. So these are quite strange conclusions, but this is the current best model there is. So yes, man's reach exceeds his grasp, I suppose. This is the end of the cosmology section. Now let's go to the light note that I mentioned. If we look tomorrow at dawn at 4:30 a.m., we have Saturn and Jupiter high above the horizon in south-southeast, in the south-southeastern direction, and they're high above the horizon. So if the sky is clear, it would be a good idea to look out for them. Mars is lower in the sky, about 8 degrees in the direction southeast. Recall last week the moon was in the way, and it was really blocking the view of the planets. But now it's no longer there, as we also anticipated. Something that's perhaps interesting to everyone who's observing the Ramadan is what will happen in the coming days. For instance, the 22nd of May, around 10:40 a.m. I have here. Now these are predictions. One has to recall. We have the sun and the moon, and on the 22nd at 10:40 a.m. really the moon is near the sun, but still to the right. So one has a waning crescent. But what happens at the same day at 3:15 p.m. is that the moon is overtaking the sun, and so it's coming close to a new moon. And by the end of the day, this is the horizon, this is the sun and the moon, and we know the sun to be setting in west, and in a westward direction, and we see that the moon has overtaken the sun, and so it's on the other side. So it is really a waxing crescent on the 22nd, or sunset. But we really have no prospect of seeing this new moon. The moon is, in this case, lower on the sky, and so it will set before the sun. And we really need the sun to set in order to see the moon, because the sun is overpowering everything. Now, on the 23rd of May at 10:10 p.m., this is over Cambridge, the sun has set. This is the next day. The sun has set in west again, in a westwards direction, and the moon is above the sun. So here we have it. Sorry, it should have said to the left of the sun. The moon is to the left of the sun, and it is above the sun. So here the sun is setting below the horizon, and there is a small prospect. There's not much, but small prospect of seeing it. Now that was without the atmosphere. With the atmosphere, this becomes more complicated, of course, much brighter, since the atmosphere is scattering all the light, which we learned from lecture 3. So the sun has set below the horizon, the moon is above the sun, and the moon is to the left of the sun. We have a waxing crescent, so we have a new moon. That was Cambridge. We normally hear that having a different position can help us observe the new moon. And so here I've taken Senegal, Dakar, We look at the evening, the same evening, 23rd of May, 9:40 p.m. The angles between the sun and the moon are still the same, as one will note here, but they have a different slant with respect to the horizon. As you can see, it's more it's more vertical with respect to the horizon in Dakar. And so this gives us better prospects for observing the moon because now the moon is higher in the sky when the sun sets. Now, note that these are all expectations and estimates. This is not the real sky. And I think it is not controversial to say that it's best to observe to confirm. On the expected day of Eid, there is another astronomical event that might be of interest to you. This is on. This is at. This is again 10:30, so after the sun has set. We again, of course, now the sun is the moon is much to the left of the sun, so we have a more advanced waxing crescent, a new lunar month. Mercury and Venus are near the moon and above the horizon. Since the sun is below the horizon, it should be possible to see Mercury. This is not always it's not always possible. So this is quite. It should be possible to see Mercury. And the problem with Mercury in general is, of course, that the Mercury is an inner planet, and it is the closest planet to the sun. So it is never too far away from the sun. So this gives us a problem with actually observing it. But it is fortunate around this time of the year because it is at its greatest angular distance from the sun. This is the greatest angular distance from the sun is called greatest elongation, and in this case, it's to the west. The elongation is to the west, so we say greatest western elongation. There is also an eastern one, and it's about 20 degrees. And I was thinking, could one do a back of the envelope calculation of this angle? And indeed one can. So zooming out, we of course remember that there is this picture where everything is going around, or the planets are going around the sun, and Mercury is nearest to the sun, and we have Venus, which I haven't drawn, and then the Earth. And if one has a western elongation, then the Mercury is to the left. And so this angle that I denoted here is really this angle, of the angle between the sun and Mercury. Can we estimate it? There is a rule of thumb that if the Earth is if the ratio of the radius of Mercury to the radius of the Earth's orbit is 4 to 10. So this is a triangle that has a side 4, and this is 10. So we can estimate this angle by trigonometric relation, the inverse tangent of 4/10, and indeed it gives us 22 degrees. So all these pictures that I was drawing in lecture 1 and 2 in particular have not been in vain, it seems. So do see if you can catch it on the expected day of Eid. So this is the end of the lecture series. We have come a long way, thousands or millennia of human thought and reflections on the sky that began by looking at the night and day, the motion of the moon and sun and the planets, the ecliptic. We saw the seasons. We then we saw that there was. We then went to try to explain the motions with Newton, and saw that really the laws were the same on Earth as in the sky, and so there was a unification there. There was lecture 2, and we saw that all these planets and satellites, they have regular orbits, and that they can be analyzed and they can be calculated. And then in lecture 3, we were looking at light and looking at different phenomena with light. What was prominent was this discovery of Ole Römer, that by using the fact that using observations of Jupiter's moons, one could if light has a finite speed, there is a delay, that one could determine the speed of light by just by observing astronomical phenomena. Then we looked at different properties of light on Earth, and we again saw that we saw that light was an electromagnetic phenomenon, and so we had a constant. We saw that the electromagnetic waves were constant. They had a constant speed, the speed of light, that Ole Römer determined, not so precisely, but still determined. And then this led us to this lecture, where we have gone as far out as we could, and we have seen that all these reflections about the night sky and the heavens have led us even to a rethinking of time and a rethinking of space and a rethinking of gravity and a rethinking of the beginnings, and that we see that there is so much structure out there, that we are not alone. I mean, as the galaxy, there is not just one galaxy, and there's not just the sun is much like the other stars, and so I think that in this lecture series I have demonstrated, or I hope to have demonstrated, that we have come a long way, and I hope to have introduced you to the to modern physics. So I hope you've benefited. And please send questions and comments to Amel at nbi.dk. I still have there's still some questions that I've not had time to answer, but I hope to answer them after I finish this this lecture. Please consider donating to help Cambridge Muslim College continue its service to the Muslim community. Alhamdulillah. Some words of thanks. I would like to thank Sheikh Abdul Hakim Murad, firstly for having me as a visitor to Cambridge Muslim College, and then also suggesting these lectures and having a look at them and reading and improving them. I would like to thank Tariq Chow for the behind-the-scenes work that you don't see, but that has been crucial to have this this lecture go online. I would like to thank the staff and the students of Cambridge Muslim College. It has been a pleasure getting to know them. I would like to thank Milan Lukic for providing some of the illustrations for lectures 1 and 2. I would like to thank Boumediene Hamzi and Rahma Al-Farsi for having a look at my lectures and hearing them before you got to hear them and suggesting changes. So thank you for watching. I wish you a blessed final week of the Ramadan. May God receive your prayers, fasting, and good deeds. Assalamu alaikum wa rahmatullah wa barakatuh.